Welcome back, dear students, to the tetrahedron chemistry classes. So in today's class, I am going to solve another problem based on the combined spectral problems. And this problem I have again taken from the organic spectroscopy book by Pavel, Lamped and Krech. And this is the problem number 30. And this problem is particularly important for the students who want to learn the NMR spectroscopy in the depth. Okay, because in this particular problem, we will use the Dept Nmr spectrum as well, along with the proton NMR spectrum and the carbon spectrum. Okay, carbon spectrum is not there, but certain values are there. Okay, so this problem is going to be very, very important. This compound has the molecular formula of C6H12O, which I have written over there. Interpret the pattern centering on 1.3 and 1.5 ppm in the proton NMR spectrum. You have been asked only one thing, that you need to or you have to interpret this particular NMR pattern, which is in between the 1.3 and the 1.58 parts per million. That means this particular thing you need to explain why this typical splitting pattern is here. Okay, that's why this problem is going to be very, very special for you. Okay, so what we'll do, first of all, we'll calculate the index of hydrogen deficiency or the hydrogen deficiency index. HDI formula is the 2C plus 2 plus N minus H minus X over 2. So here 6 carbons are there. So 2 into 6, that will make 12, and plus 2, that is 14. No nitrogen is present, 0. 12 hydrogens are present, minus 12. No halogens are there, 0 over 2, that is 14 minus 12 by 2, that is 2 by 2 equals to 1. So index of hydrogen deficiency in this particular formula we have calculated as 1, and this 1 indicates that your molecule may have the one ring, or it may have a double bonds. But in the IR spectrum, you can see here a band resonating at 1715 centimeter inverse, and it's a very sharp band and very strong band. Okay, and this 1715 centimeter inverse is a typical value for the aliphatic ketone. That means carbonyl carbon is present here. Okay, this carbonyl group belongs to the aliphatic ketone. This is the typical value. So you have identified this C double bond O. Okay, and then if you quickly see your proton NMR spectrum, so you are having this particular singlet over there, and this singlet is resonating at somewhere around at 2.0 ppm. It clearly indicates that its integration is quite high. That means these are the 3 protons, and it is these 3 protons are giving only one singlet. It clearly indicates that it is connected with the carbonyl group, as its chemical shift is also. So this fragment you have confirmed, CH3 C double bond O. This you have confirmed. Okay. Apart from this particular fragment CH3 C double bond O, nothing much is there in the spectrum to get idea about the other units present in the, or other groups present in the molecule. Whenever you have been given in your data this Dept NMR, always try to interpret this Dept NMR first. You must have an idea about the interpretation of the Dept NMR spectrum. So this is the data for the Dept NMR, and I hope you understand what is the meaning of the Dept. DEPT, distortionless enhancement of polarization transfer. Okay, this is a special technique in the NMR. This will give you the idea about the types of the carbons present in the molecule, whether your carbon is connected with the one hydrogen, it is connected with the two hydrogen, or it is connected with the three hydrogens. Okay, so first of all, you see here Dept 135 is given here, and these are the chemical shift values for the typical carbon, and this 200 is 13. It is the value of carbonyl carbon. Your remaining carbons are also there. 6 carbons are there, so 6 chemical shift are also there. One Dept 135. So what information we can get from the Dept 135? See, your molecule may have this particular kind of the carbon. Your molecule may have this particular kind of the carbon, which is connected with the two hydrogen, and then the three hydrogens. These kinds of three hydrogens are possible whenever you are talking about the Dept NMR spectrum. So this particular CH, right, this will give you the peak on the positive side. That means usual NMR peak. and the carbon which is having the 3 hydrogens over there, it will also give you the positive peak. That means your normal upright peak. Whenever your CH2 is present in the molecule, you will have the negative peak. Negative peak means peak on the bottom side. Say for example, these peaks may belong to either CH3 or CH, but this negative peak always belongs to CH2, right? So this information we can get from the depth 135 NMR. So you can see here uh, positive peak, positive peak, positive peak, positive peak. 4 positive peaks are there. In the depth, you can see here in the DEPT 135, 4 positive peaks. 4 positive peaks. 4 positive peaks means these 4 may be your CH, 3CH or 1CH3 or 3CH3 or 1CH or 2CH or 2CH3, any combination could be possible, right? So these things are there. And then you are having, you can see here, this is your negative peak. Negative peak means your carbon which is connected with the 2 hydrogen, negative peak, okay? So one negative peak is there, so I'm writing, it clearly indicates that your molecule is also having CH2 group, okay? Now, then you can see your next one, your depth 90. So what information we can get from the depth 90 NMR spectrum? It is very, very important. Remember, whenever this depth 90, whenever the peak is present on the depth 90, it clearly indicates the methine hydrogen. That means CH is also present in your molecule. And this is no peak, no peak, no peak, no peak, no peak. That means only one carbon is like that, which is having the one hydrogen attached. You have confirmed only one CH. So what you left with, that means your molecule is having one CH here and 3 CH3. So now you have confirmed many things. So what things you have confirmed so far? I am writing here. You have confirmed the presence of carbon double bond oxygen connected with the CH3. This you have confirmed earlier. Presence of another 2 CH3 groups. This you have also confirmed. And then you have confirmed one of the CH2 group from the depth NMR spectrum. This is the negative peak. This negative is due to the CH2, right? And then from the depth 90, you have confirmed this CH. So you're having these things. These things you are having, okay? Now what you can do, you can put them together to get the correct structure of the molecule. I hope you understood these much of things quite clearly, okay? Now what we can do, we can put these pieces together to get the correct structure of the molecule. This is something very, very important. And one more important thing you can observe here, in this particular spectrum, where in the bottom part your depth NMR data is given, right? In the upper part, you have been given a triplet here, okay, and a doublet. Triplet and doublet you are having. So triplet, how you can get your triplet? Triplet you can get in this manner only. Your CH3 when connected with the CH2, okay, that mean it will give you what? A triplet. So whenever you are calculating the splitting pattern of any methyl group, right? So say for example, you are calculating the splitting pattern or splitting of the peaks for these particular 3 hydrogens. So you need to look on the hydrogens present on the neighboring carbon. So if you want to calculate the splitting pattern of these 3 hydrogens, you need to check the number of the hydrogens on the neighboring carbon. So neighboring carbon is this one and it is having 2 hydrogens only. So what you can do, you can apply the n plus 1 rule, where n is the 2 which are the neighboring hydrogens plus 1, that will give you 3. So this is how you can get the triplet. So now you have confirmed this thing, and now you have confirmed the connection in between these two. That means you are having CH3 and CH2 as well. Okay, and then you are having one CH this one and CH3 this one. Okay, so how we can connect these things? You can take the screenshot of this one. You are having this CH3, there is no problem in that, and then you are having CH2, again no problem, and then you are having this CH. Okay, along with the CH you are having this carbon double bond oxygen and then CH3. These things are here. Okay, what you left with? You left with this methyl group. You left with this methyl group. So you can connect this methyl group over there. Say this is carbon 1, carbon 2, carbon 3, carbon 4 and carbon 5. So it is where 3 methyl pentane 2 one. So this structure could be the answer. Okay, but we'll verify how we are having this particular answer. Okay, so first of all we need to check the splitting pattern. See, this will give you the singlet. S I am writing here. Okay, and say this one, this will give you what? A triplet. And then you are having this. See this, why this is producing a singlet? Because there are no hydrogens present on the neighboring carbon. And why it is giving a triplet? As I explained here, because in the neighbor you are having the two hydrogens. And if you want to calculate the splitting pattern of these three methyl groups, so you need to look on the number of the hydrogens present on the neighboring carbon. So your neighboring carbon is having one hydrogen only. You will apply n plus 1 rule. So you can write n plus 1. That will give you what? 1 plus 1 equals to 2. 2 means doublet. So this will produce a doublet. This will produce a doublet. And you see, this doublet you are having here. This doublet you are having here. So many things you have confirmed. You left with the interpretation of this CH2 group, and then you left with the interpretation of this CH group. Rest you all have decided already, right? This singlet, this doublet, and this triplet. Now, if I go back further, say this is the typical splitting pattern which you need to decide, and this is the typical splitting pattern which you need to decide. Okay, so what I can do, I can draw the previous structure very quickly. First of all, we'll decide the chemical shift, okay, for the hydrogens present in the molecule. So I'm telling you, this would be the most downfield signal. It is most downfield signal. Most downfield signal. Why? Because this hydrogen is connected with the carbonyl group, and carbonyl group is the electron withdrawing group. So it will deshield these hydrogens, and deshielding always causing the downfield shift. So in the entire molecule, this signal would be the most downfield signal. So straightforward, you can jump up to the conclusion that this particular splitting pattern is due to the presence of the CH. Okay, later we will decide how we are having this particular set of the splitting pattern. And then you are having, say, next one is this one. This is your second most, not this one, very sorry. Now you can see this particular one, this is the second most downfield. Second most downfield signal. Why second most downfield signal? Because this is the alpha carbon and these hydrogens are alpha hydrogens. Similarly, this hydrogen is also the alpha hydrogens. So this carbonyl group will deshield the hydrogens of this methine as well as this methyl group. But this methyl group is having the three hydrogens, so the deshielding would be little bit low for these three hydrogens when compared to this particular hydrogen. So this is the second downfield signal. That means you can say this signal is due to the presence of CH3 which is connected with the carbonyl group, right? You can see, right? And then next one is, you can say, this particular one. This is where beta carbon, and this is also the beta carbon, right? But this would be your third most downfield because the number is 2. You can say this is alpha, this is beta, this is alpha, this is also beta. So both these are beta, but you can see this beta carbon is having only 2 hydrogens, so the deshielding effect will be higher on these 2 hydrogen when compared to these 3 hydrogens. So this would be your third most downfield signal. So I'm writing third most downfield signal. Third most downfield signal. It clearly indicates that these particular signals is due to the CH2 group. This typical pattern is due to this CH2 group, right? And you can see this would be your most upfield signal. This is where most upfield. Why most upfield? Because it is very far away from this carbonyl group, so it will be very upfield. That means the highest that means the lowest delta ppm, lowest value of the chemical shift will be present, will that mean lowest value of the chemical shift would be there for this particular methyl group, and it will produce a triplet, so this CH3. So this signal A basically is belong to the this particular CH3, right? And then you left with this doublet. How we are getting this particular doublet? This doublet is due to this methyl group, right? So this methyl group which is connected with this one. Okay, so what we can do? We can straightforward connect this. Okay, this signal is due to this one, and this triplet is due to this one. I hope this is quite clear. Now we need to understand the splitting pattern of this CH2 group. This is very important, and this will give you the idea how we can interpret the NMR spectrum in the different way. Okay, so you can see here what I can do. I can write like this. Say this is my CH2 group, and this is connected with the CH here, and here it is connected with the CH3, right? And we are going to decide the splitting pattern of this one. So what will happen? This CH2 can couple with this hydrogen, right? And this can also couple with this hydrogens, right? But the question is that whenever these two different kinds of the sets of the hydrogens are there, and this CH2 is coupling with both of them, and with which actually this CH2 will couple first, this will be decided by the value of the coupling constant. You can very easily calculate the coupling constant from here to here. So if I calculate the coupling constant, say between these two peaks, right? Between these two peaks, I am calculating the coupling constant. So this value is your 472.77, and this particular value is 465.36. If you subtract this, then you will get 1. Similarly, in the second one, say for example, if you want to calculate the coupling constant, so you will take this particular value of 395.92, and this is the second coupling constant, which is your 388.98, right? So this will give you 4, and then 18 minus 9 is 9. Higher the value of the coupling constant, first it will couple with the another hydrogen, right? Since both the values are very close, approximately 7 hertz. Coupling constant for both of them is 7 hertz, but not exactly 7 hertz. If these two values are exactly 7 hertz, then definitely what will happen? You will get the quintet. Okay, say for example, this coupling constant and this coupling constant is having the identical value, so you will get a quintet. How quintet? 3 hydrogens are here, 1 hydrogen is here, so 3 plus 1, that is 4. Or if you apply the n plus 1 rule, n plus 1, that will give you 4 plus 1, and it will give you the 5, and this will be your quintet. But this is possible only when these two coupling constant are exactly same or the identical. They are not identical, but they are somewhat similar. So it means that you will not get quintet, you will get some other splitting pattern. So what is that other splitting pattern? We need to decide this thing. Okay, so I am telling you what is happening here. Actually, this particular CH2 will produce DQ. It will produce your DQ, and the full form of the DQ is doublet of quartet. Why doublet of quadrate? I'm telling you, the value of the coupling constant. Say for example, I can mark this. Say this is my A, this is my B, this is my C. Okay, so this coupling constant is little bit higher. However, they have the roughly same value of the 7 hertz, but I'm telling you this value is little bit higher, right? So what will happen? This CH2 will couple with this hydrogen first. Since the neighboring hydrogen is only one, you will get a doublet here. What you will get? You will get a doublet. So I'm drawing a doublet here. JAB. What I have written over there? JAB. What is the meaning of JAB? These A hydrogens are coupling with the B. So you are getting a doublet. This one. Now what will happen? Each of the peak of the doublet, that means these two peaks, right? This peak will couple with this methyl group, right? And then your second peak will also couple with this methyl group. Each peak will split into a quadrate. You are having these two peaks which I have drawn, and then you see neighboring hydrogens are 3. So again you will apply n plus 1 rule. This will give you 3 plus 1, that is 4. That means each of them will now split into the two sets of the 4 peaks. You can draw like, and this is basically your JAC. Why JAC? Previously it was coupled with this one JAB. Now it is coupling with this one, that is JAC. Okay, and you are having this 1 2 3 4 5 6 7 8. This pattern you are having. I'm drawing the peaks here. So this will produce a pattern like that. One, they are quadrates. This is known as doublet of quadrates. So this CH2, right? This CH2 will produce a doublet of quadrate. So this particular region, right? This is basically the signal which is due to the presence of this CH2 group. Now in the expansion, I'm going to this particular expansion, right? You see this expansion which I have shown you here. I have shown you only 8 peaks, right? 1, 2, 3, 4, 5, 6, 7, 8. But here you can see the number of peaks are quite large. 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Many peaks are there. You can see the complex splitting pattern. These lines we have calculated theoretically. So somehow we are very close to this particular pattern, but not exactly to this particular pattern. But this is the only possible way by which you can get this particular pattern of the peaks. There is no other way to get this particular pattern. Please remember. Okay. So now if I go back, this CH, why we are getting this peak? So if I go to the expansion of this one, so 1, 2, 3, 4, 5, 6. Total 6 peaks I am getting. So this is my CH3, CH, and then CH2. What I can do, I can mark it as, say this is my hydrogen A, and this is my hydrogen B, and this is my hydrogen C. Now again what you can do, say this CH can couple with this CH2, this can also couple with this CH3, but I am telling you this value of the CH when coupled with the CH3, this coupling constant is slightly higher than the coupling constant with this CH2. So basically this J value is little bit higher. So this hydrogen will couple first with this particular 3 hydrogens. So if you apply the n plus 1 rule, okay, for a splitting pattern of this one, 3 neighboring hydrogens plus 1 equals to 4. So this will produce a quadrate, right? This will produce a quadrate. So I am drawing your quadrate. This quadrate, each of the line or of the quadrate will couple with this CH2, and again you will apply the n plus 1 rule. So now the neighboring hydrogens are 2 connected with this one hydrogen. This will give you 3. So each of the peak will now split into the 3. So how many peaks I am getting? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 peaks basically we should get. How I am drawing this 1, 2, but we are getting only these much of 6 lines or the 6 peaks. This is due to the overlapping of the peaks. This is due to the overlapping of peaks due to similar j values. Okay, this structure is more consistent with the data given in the IR spectrum, proton NMR spectrum, and as well as the splitting pattern, right? This is the best possible explanation for this particular molecule. So if you want, then you can decide the value of the carbon chemical shift as well. Say for this carbon, the value is 213 picometer. Okay, so this is most upfield signal. This is 16 ppm, right? And this one is the second most downfield signal after 213. So this will resonate at 49 ppm. Please remember, this is resonate 49 ppm. Okay, and then this will resonate at 28 ppm. Okay, and then you are having this particular one. This will resonate at 26 ppm. And finally, uh, sorry, not this one is not 16. This will resonate at 12 ppm. I'm sorry, 12 ppm, and this will resonate at 16 ppm. So this is how you can solve the typical problems with the help of the Dept NMR data. Okay, I hope you understood the things. Okay, if you are getting something from the video, if I am adding a little bit value to your knowledge, then please like the video and subscribe the tetrahedron chemistry classes, and do share with your friends as well. Okay, I'll meet you in the next class with some other problem. Thank you very much.